Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Glad to be here for this one. It's a topic that keeps a lot of engineers up at night.
Oh, absolutely. I mean, I want you to just imagine standing next to a massive 3-ton industrial power generation turbine.
Right, just a massive piece of machinery.
Yeah, and it's spinning at 10,000 revolutions per minute. It sounds like a jet engine. The floor beneath your boots is humming, and, everything seems perfectly fine.
But it's usually not.
Exactly. Because hidden inside the mathematics of that machine, there's this microscopic miscalculation in the stiffness of a single, like a rubber mount. And it's causing a resonant frequency to align perfectly with the rotor spin.
Which is pretty much a nightmare scenario.
Total nightmare. You can't see it yet, but the amplitude of the vibration inside that steel housing is like doubling every few seconds. And in exactly 2 minutes, that 3-ton piece of precision engineering is going to violently tear itself off its mounts, shatter its casing, and just send hypersonic shrapnel through a concrete wall.
I have actually seen the aftermath of failures like that, and it's not pretty.
So today, for this deep dive, we are conquering the mechanics of shock and vibration to make sure you never design that turbine.
That's the mission.
We're going to break down the biggest pain points and real-world issues engineers keep running into with this subject. We'll call out the common modeling and measurement misconceptions that ruin designs.
And there are a lot of them.
So many. And then we'll walk through a step-by-step approach to avoid these traps and answer the most common questions about optimizing designs in practice.
Right, because it's all about giving you the tools to actually optimize a design, not just on paper, but, in the messy physical world.
Exactly. But I guess to optimize a design, you first have to know exactly what kind of dynamic enemy you're fighting.
Yeah, you really can't defeat an enemy you don't properly classify. And in the realm of structural dynamics, that enemy usually takes one of 2 primary forms: vibration or shock.
Okay, so let's break those down.
Well, while they share the same underlying physics of, mass and stiffness, they are fundamentally different beasts in how they deliver destructive energy.
How so?
So vibration is an oscillation. It's this continuous, alternating transfer of energy within a mechanical system.
Like a pendulum or something.
Yeah, exactly. If we strip it down to its absolute simplest form, just think of a solid steel mass hanging from a coiled spring.
Okay, visualizing that.
You pull that mass down and let it go. The energy shifts from the potential energy stored in the stretched metal of the spring into the kinetic energy of the heavy-moving mass as it accelerates upward.
Right, and then back into potential energy as the spring compresses at the top of the stroke.
Exactly. It's a constant, ongoing conversation between kinetic and potential energy.
A conversation, I like that.
And we typically model this continuous conversation using 3 elements. You've got a mass to store kinetic energy, a spring to store potential energy, and a damper to represent the energy permanently lost to the environment through friction or heat.
So that's vibration. But shock is totally different.
Completely different. Shock does not give the structure time for a conversation.
It's just a shout.
Yeah, it's a sudden, non-periodic, and severe excitation. An impact, an explosive blast, a package dropping off a forklift, or a sudden step in velocity.
So the event is completely over before the structure even has a chance to fully react.
Right. The external force spikes and vanishes, leaving the structure to wildly deal with this massive, instantaneous injection of residual energy.
Wow. Okay, so let's unpack this taxonomy of tremors. Let's focus on vibration first because, even within that category, there are subdivisions that constantly trip people up in the field.
Oh, yeah.
We have deterministic vibration and random vibration. And then layered on top of that, we have stationary versus non-stationary environments.
And the mathematical approach you take to save your design depends entirely on getting those initial categorizations right.
So what's deterministic vibration?
A deterministic vibration follows an established, mathematically predictable pattern. If you know the past history of the vibration, you can plug it into an equation and perfectly predict its exact amplitude and direction at any designated future time.
Like whether that's 10 seconds from now or 10 years from now.
Exactly. The classic example is the vibration radiating from a rotating motor, a reciprocating engine, or like a helicopter rotor.
It's periodic. It repeats.
Yeah, the math is clean. But range vibration is the exact opposite.
Which is what a lot of people actually deal with.
Yeah, it's entirely unpredictable in its exact moment-to-moment instantaneous magnitude. You just cannot write a simple sine wave equation for it.
So how do you define it?
You can only define it in statistical terms. You use probability distributions to indicate the likelihood of certain acceleration magnitudes occurring.
Okay, so give me an example of that.
Think about the environment a rocket experiences breaking through the atmosphere at supersonic speeds.
Oh, yeah, that's got to be intense.
The acoustic energy from the rocket plume and the turbulent aerodynamic boundary layer tearing over the metal skin, it creates this broadband, chaotic rumble.
You have no idea what it's doing at any exact millisecond.
Right, you don't know exactly what the skin will be doing at millisecond number 400, but you can predict the probability that the stress will exceed the yield limit of the titanium over a 10-second window.
That statistical approach, that leads right into the stationary versus non-stationary distinction, right?
It does. A stationary vibration is one where the fundamental statistical properties, like the mean value, the overall variance, or the root mean square, they don't change over time.
So the environment is chaotic, but it's constantly chaotic in the exact same way.
Exactly. A non-stationary vibration, on the other hand, means those underlying statistical properties are actively shifting.
So sticking with a rocket.
Yeah, imagine a launch vehicle accelerating from Mach 1 to Mach 5. The dynamic pressure on the vehicle is constantly changing.
The vibration profile at minute 1 is entirely different from the vibration profile at minute 3.
Precisely.
You know, from what we see in failure analysis reports, there is a massive misconception here that completely screws up designs right out of the gate.
Oh, I know exactly what you're going to say.
Because the math for a predictable sine wave is something we all learn in, like, high school physics. Engineers have this incredibly dangerous tendency to treat all vibration as if it is stationary and deterministic.
It's the trap of mathematical convenience.
Yeah. They design their brackets and mounts to survive these clean, predictable, beautiful 50 hertz sine waves. But the physical reality of the environment is actually throwing broadband, chaotic, non-stationary random vibration at them.
We're taught harmonic motion on day 1 of physics, you know? Simple sine and cosine waves. So when an engineer looks at a complex operational environment, the psychological temptation is to approximate it as a combination of steady sine waves.
Because it makes the spreadsheet look cleaner.
Yeah, it does. But designing an aerospace component to survive a continuous single-frequency 50 hertz sine wave is completely different from designing it to survive a random broadband rumble that hits every frequency between 10 and 2000 hertz simultaneously.
And fluctuates in overall intensity.
Right. If you treat random vibration as deterministic, your fatigue cycle calculations will be wildly inaccurate.
You'll severely underestimate the cumulative damage happening at the microscopic level of the metal.
And your part will fracture in the field long before its design lifespan.
It's crazy. I picture deterministic, stationary vibration like a metronome sitting on a piano. Tick-tock, tick-tock. It never changes pace, and you know exactly where the pendulum arm will be 10 minutes from now.
That's a great way to look at it.
But non-stationary random vibration is like taking a shopping cart with a wobbly wheel, filling it with bowling balls, and driving it over a cobblestone street while simultaneously accelerating and occasionally hitting a pothole.
It is absolute chaos.
Right. But if random vibration is totally unpredictable and changes moment to moment, like that shopping cart, how do we even begin to mathematically model it without just blindly guessing and hoping the metal holds?
Well, we have to abandon the quest for absolute certainty and embrace the mathematics of probability.
Okay.
We stop asking the impossible question like, what will the exact displacement of this bracket be at exactly 3.2 seconds?
Because you just can't know.
You can't. Instead, we ask, what is the probability that the displacement will exceed 2 millimeters during this entire 5-minute flight window?
And how do we do that?
To do this, we rely heavily on something called the ergodic hypothesis.
The ergodic hypothesis.
Yeah, it's a fundamental concept in statistical mechanics. It states that for a stationary random process, taking time averages from a single very long sample record will give you the exact same statistical properties as taking an ensemble average across multiple different sample records at a single instant in time.
Wait, let's freeze right there. The ergodic hypothesis. That sounds like something out of a theoretical physics textbook. What does that actually mean for an engineer trying to measure vibration on a physical prototype?
Think of it like a casino.
Okay, I'm with you.
Suppose you want to know the statistical probability of a coin landing on heads. You have 2 ways to figure this out.
Right.
The first way is to gather an ensemble. You get 1 million people, give them each a coin, and have them all flip it at the exact same moment.
Wow, okay.
You take a snapshot of that single millisecond, count the heads, and get your probability. That's an ensemble average.
And the second way?
The second way is to take just one person, give them one coin, and have them flip it 1 million times over the course of a year. You average those results over time.
And the hypothesis says?
The ergodic hypothesis says that for a stationary random environment, those two methods yield the exact same statistical answer.
Oh, I see.
In engineering terms, it means we don't have to launch 10,000 rockets simultaneously to understand the vibration environment.
That would be expensive.
Very. We can just put a sensor on one rocket, record the data over a sufficiently long period of time, and use that single time history to confidently predict the statistical probability of failure for every future rocket.
That is incredibly practical. But to even begin applying those advanced statistics, we have to build mathematical models of the physical structures themselves to see how they react to that input.
Exactly.
Which takes us out of the environment and directly into the hardware. We have to map the unpredictable input to a mathematical model of our system, but building those models is where theoretical traps are just everywhere.
Oh, they really are. And the foundation of all structural dynamics begins by defining the degrees of freedom.
Right, SDOF and MDOF.
Yes. A single degree of freedom system, or SDOF, is the simplest possible mathematical abstraction. It means you only need one single independent coordinate to completely define the geometrical position of the entire system at any given instant in time.
Like a rigid block constrained to move only perfectly up and down on a single coil spring.
Exactly. That's an SDOF model. You only need to know its vertical year coordinate.
But a physical structure, like the wing of an airplane.
It's a continuous system. It's made of billions of molecules, meaning it has an infinite number of degrees of freedom. It can bend, twist, shear, and warp in countless directions simultaneously.
Which is impossible to calculate.
Because the math for infinite degrees of freedom is unsolvable in practical engineering, we discretize the continuous structure. We chop it up into a multiple degree of freedom model, or an MDOF system, using a finite number of lumped masses, springs, and dampers.
What fascinates me is how universal the physics are once you break it down into those lumped elements.
Yeah.
Like the math translates flawlessly between something moving in a straight line and something spinning in a circle. There are direct analogies here.
Yeah, the equations of motion are structurally identical, only the variables wear different clothes.
I love that phrasing.
In translational linear motion, the core elements are force, mass, and linear displacement. If you transition to rotational motion, say, analyzing the vibration of a ship's propeller shaft, the mathematical analog to linear force is torque.
Okay, torque makes sense, and mass.
The analog to physical mass is the mass moment of inertia, which accounts for how that mass is distributed around the axis of rotation.
Right.
And the analog to linear displacement is angular displacement, usually measured in radians. If you deeply understand the differential equations governing how a simple block on a spring oscillates up and down, you inherently understand the mathematics of how a massive flywheel on a twisting steel shaft oscillates back and forth.
So whether we are talking about a linear spring or a twisting shaft, what does this actually mean for calculating the baseline pulse of the system? I'm talking about the natural frequency.
Ah, the undamped natural frequency.
Huh?
It is the single most critical calculation in all of mechanical vibration analysis, period. It's the frequency at which the system naturally wants to oscillate if you strike it once and let it ring, assuming absolutely no damping or energy loss in the universe.
And for our listeners following along with the physics, the math here is foundational. Omega n equals the square root of k divided by m.
Exactly. That is the angular natural frequency, omega.
And it is determined entirely by the ratio of the system's spring stiffness, k, to its mass, m.
Yep, just k and m.
Let's zoom in right here because this exact equation, omega n equals the square root of k divided by m, is where one of the most insidious multi-million-dollar traps in mechanical engineering is hiding in plain sight.
It's the static versus dynamic trap.
It's the dangerous assumption that static deflection always equals dynamic stiffness.
This is a classic catastrophic error that engineers make constantly, particularly when working with elastomers, isolators, or rubber mounts.
Walk us through how this happens.
Let's say an engineer is designing a suspension system for a delicate piece of electronics inside a military vehicle. They need to know the stiffness, K of a rubber isolation mount so they can plug it into that equation and calculate the natural frequency of their system.
Right, so they need the K value.
So what do? They take the rubber mount into the lab, place a heavy static weight on it, measure with a ruler how many millimeters the rubber compresses, and divide the force of the weight by that displacement to get K.
And then they just plug that static stiffness into the dynamic equation.
And by doing that, they have just compromised the entire design.
Completely compromised it.
Yeah. Rubber, synthetic elastomers, and many other complex materials do not behave the same way under a rapidly oscillating dynamic load as they do under a slow, static, resting load.
Why is that?
At a molecular level, rubber is made of long, tangled polymer chains. When you push on them slowly, those chains have time to slide past each other and reorient. That gives you a low static stiffness.
Okay, that makes sense.
But when you strike them rapidly with a dynamic vibration, those long polymer chains do not have the time to disentangle. They lock up.
Oh, wow.
They resist the rapid motion with significantly more force. This means the dynamic stiffness of a rubber mount can be vastly different, often an order of magnitude higher than its static stiffness.
An order of magnitude.
Easily. If you use the static stiffness from your lab ruler measurement in your dynamic calculation, your predicted natural frequency will be entirely wrong.
You will design the system thinking your electronics are perfectly isolated from the low-frequency rumble of the vehicle's engine.
But in reality, your actual dynamic natural frequency is much higher, and it might be perfectly aligned with the destructive forces of the environment.
The analogy I use for this trap is testing a mattress.
Oh, let's hear it.
Imagine you want to test how stiff a memory foam mattress is. If you gently sit on the edge of the bed, the foam sinks in slowly. The polymer chains have time to move.
Right, low static stiffness.
You measure that deep sinkhole, calculate your K value, and you think, okay, this is a very soft mattress. That is your static stiffness. But if you climb up to the top rope of a wrestling ring and drop an elbow onto that exact same mattress,
It's not going to end well.
not at all. The material reacts completely differently to that sudden dynamic impact. The air can't escape the foam fast enough, the polymers lock up, and the mattress pushes back with the rigidity of a wooden board.
That's a great visual.
If you calculated the safety of your jump based on gently sitting down, you are going to shatter your collarbone.
Exactly.
But I have to push back on this whole modeling philosophy. We keep talking about a mass and a spring. Why do we even rely on single degree of freedom models with basic isolated masses and springs when a real-world machine like a naval submarine or commercial jetliner has millions of complex interconnected parts? It feels like we're trying to model a hurricane using a single drop of water.
I get that. It sounds totally reductive. But we use these highly simplified single degree of freedom models because they represent the fundamental independent building blocks of something called modal analysis.
Modal analysis.
Yeah, even an incredibly complex structure with millions of parts, like a submarine pressure hull, can be mathematically decoupled into a series of individual, completely independent, single degree of freedom systems.
Really? Just broken down into simple springs and masses.
Exactly. Each one of those simplified systems represents one specific normal mode of vibration. The submarine has a mode where it bends like a banana. It has another mode where it twists like a towel. It has another mode where it breathes in and out like a lung.
And we can model each of those independently.
By understanding the simple mass-spring math, we can perfectly model each of those individual modes. The total, chaotic, complex physical response of the entire submarine to an underwater explosion is mathematically just the superposition, the linear sum of all those simple models reacting simultaneously.
That is wild. However, the stakes are incredibly high.
Very high.
If you miscalculate the natural frequency of even one of those fundamental modes because you use static stiffness instead of dynamic stiffness, you leave a gap in your defenses. And that gap opens the door to the most destructive phenomenon in mechanical engineering.
The real-world wrecking ball, resonance.
Resonance. Once you miscalculate that natural frequency, resonance will find the flaw in your math and tear the metal apart.
Resonance is the phenomenon that haunts structural engineers. It occurs in forced vibration. When the frequency of the external dynamic force acting on your system, whether that is the wind pushing on a bridge or the spinning of a motor, exactly matches the internal natural frequency of your system, something terrifying happens physically.
The phase relationship aligns.
Perfectly. The phase relationship between the input force and the structure's velocity aligns perfectly. This means that every single cycle, the external force is pushing the structure exactly when the structure already wants to move in that direction.
The energy just compounds.
The energy from the force builds up, cycle after cycle, accumulating inside the system. The amplitude of the physical vibration grows continuously, limited only by the amount of damping or energy dissipation in the system.
And if there isn't enough damping?
If the damping is low, the structure will literally shake itself to pieces.
The ultimate historical case study for this is the Tacoma Narrows Bridge collapse in 1940, right? The footage of that bridge twisting like a wet noodle before snapping and falling into the river is burned into the brain of every first-year engineering student.
The Tacoma Narrows Bridge is the perfect visceral example of what happens when massive amounts of external energy align with the natural frequency of a large structure.
Though it's slightly more complex than basic resonance, right?
Technically, yes. The bridge collapse was a complex aeroelastic flutter phenomenon driven by wind vortices, but the core underlying principle of destructive energy accumulation is identical to the classic resonance.
The wind flowing over the bridge deck created alternating vortices of low pressure that pushed the bridge up and down.
And as the bridge twisted, it changed the aerodynamics, which amplified the vortices, which amplified the twisting. The energy kept feeding into the torsional natural frequency of the bridge.
Because the steel and concrete structure had very little inherent damping to dissipate that energy.
Right, so the amplitude of the twisting grew until the structural yield limits of the suspension cables and the deck girders were exceeded. It is the wrecking ball that destroys bridges, shatters turbine blades, and cracks building foundations during earthquakes.
And we measure exactly how sharp or severe this resonance is using a mathematical parameter called the quality factor, or Q.
Yes, Q is the parameter that quantifies the frequency selectivity or the sharpness of the resonance peak. It tells you how much the input vibration will be amplified when you hit that exact resonant frequency.
And what's the math for Q?
Mathematically, Q equals 1 divided by the quantity of 2 times zeta.
Zeta being the damping ratio.
Exactly. Zeta is the damping ratio, which is the fraction of critical damping present in the system.
Let's define critical damping real quick before we move on, because that is an important baseline.
Critical damping is the exact, specific amount of damping required to return a displaced system to its resting equilibrium position as fast as possible without any oscillation at all.
So if you push a swinging door and it slowly closes and stops exactly at the center latch without swinging past it?
That door is critically damped.
On it.
But most structural systems, like airplane wings or steel buildings, are incredibly underdamped. Their zeta value is far less than 1.
So zeta is a very small number. The denominator in our Q equation, 2 times zeta, is also a very small number.
And dividing 1 by a very small number means the Q factor becomes very large.
And a large Q factor is bad news.
Very bad. A large Q factor physically manifests as a massive, towering amplification of the vibration precisely at resonance. If you have a Q of 50, an input vibration of 1 g of acceleration will be amplified into 50 g's of acceleration on your component.
I have always found the nomenclature of the quality factor to be deeply, darkly ironic.
Oh, completely.
In everyday human life, if something has a high quality factor, you assume it's a beautifully made, durable product. But in structural dynamics, if your multi-million-dollar satellite component has a high-quality Q factor, it basically means it is a highly efficient energy accumulator with a very high probability of vibrating itself into space dust.
Yeah, you really don't want a high Q.
So to survive this wrecking ball, we have to optimize the design by adding damping. What are the physical mechanisms we can use?
In practice, we generally classify energy dissipation into 3 distinct types of damping. First is viscous damping.
Fluid friction.
Right. Imagine the shock absorber on your car, which is essentially a piston pushing through a cylinder filled with thick oil. As the piston moves, the fluid is forced through tiny orifices, generating fluid shear forces.
Turning kinetic energy into heat.
Exactly. It converts the kinetic energy of the motion into thermal energy, heating up the oil. The defining mathematical characteristic of viscous damping is that the damping force is directly proportional to the velocity of the motion.
So the faster you try to push the piston, the harder the fluid pushes back.
Yep.
The second type is Coulomb damping, which is also known as dry friction. This is completely different from a fluid.
Yes, Coulomb damping is the sliding of 2 dry, unlubricated surfaces against each other. Imagine a heavy steel block sliding across a concrete floor.
Okay.
At a microscopic level, both the steel and the concrete are not smooth. They are covered in tiny, jagged peaks and valleys called asperities. As the surfaces slide, these microscopic peaks crash into each other, cold weld together, and then shear apart.
And breaking those microwelds dissipates energy as heat.
The defining characteristic here is that unlike viscous damping, the Coulomb damping force is constant. It is completely independent of how fast the block is sliding or how far it slides.
It only depends on the weight and friction.
Right. It only depends on the normal force, how heavy the block is, and the kinetic coefficient of friction between the two specific materials.
And the third one, which seems to cause the most mathematical trouble, is structural damping. This doesn't involve fluids or sliding parts. This comes from within the solid material itself.
Structural damping, which is also called hysteretic damping, is the energy dissipated by internal friction within the molecular structure of a material as it dynamically bends, flexes, and strains.
So every time you bend a piece of metal, the atomic lattice is deforming.
Exactly. When the metal strains under a load, it absorbs potential energy. When the load is removed and the metal relaxes back to its original shape, it releases that energy.
But not all of it.
No, not all of it. A tiny fraction of that energy is lost as internal heat due to the molecular friction. If you plot the stress versus the strain over a full cycle of vibration, the curves going up and coming down do not perfectly overlap.
They form that hysteresis loop.
They form an ellipse called a hysteresis loop. The area inside that loop represents the energy permanently lost to heat per cycle.
And here is where another massive modeling misconception completely derails the optimization process. Engineers often assume that structural damping inside a piece of steel behaves mathematically, just like viscous damping inside an oil dashpot across all frequencies.
This is a critical error that leads to catastrophic high-frequency failures.
Because they're completely different mechanisms.
Right. With true viscous damping, the oil dashpot, the energy dissipated per cycle increases linearly with the frequency of the vibration. The faster the oscillation, the more energy the fluid shears absorb.
But solid materials don't work that way.
No, decades of experimental physical evidence show that structural hysteresis loss, the energy dissipated internally by solid materials like steel or aluminum, is largely independent of the frequency.
It depends on the amplitude.
Exactly. The internal atomic friction depends on the amplitude of the displacement, how far you bend the metal, not on how many times per second you are bending it.
So if an engineer forces the mathematical model to treat solid steel like it's a fluid dashpot, what happens to their physical prototype?
If you treat structural damping as if it were a viscous fluid in your finite element analysis software, the underlying equations will automatically predict that the damping force gets stronger and stronger as the frequency goes higher.
That sounds dangerous.
It is. You will look at the colorful stress plots on your computer simulation and think, excellent, at 1000 hertz, my structure is heavily damped and totally safe from resonance.
But in physical reality, the structural damping of the steel is constant. It didn't increase with frequency.
Your simulation will show a massive safety margin, but your physical prototype on the shaker table will experience explosive fatigue failure at those high frequencies because the actual physical damping was vastly lower than your viscous mathematical model predicted.
So how do you fix it in the math?
To fix this, you cannot use a simple viscous coefficient. We have to introduce a specific structural damping parameter, often denoted mathematically as a complex stiffness modifier, to force the equations to keep the damping force invariant with frequency.
I see. But wait, let me look at this from a high-level design perspective. If adding damping prevents this wrecking ball resonance and absorbs all this destructive energy by turning it into heat, why don't we just slather every single structural component in heavy rubber, viscoelastic goo, and fluid dashpots and call it a day? Why isn't maximum damping always the ultimate goal?
That is the instinctive reaction, but structural dynamics is always a game of trade-offs.
Trade-offs.
Always. First, there is the fundamental thermodynamic issue. Damping does not magically erase energy from the universe. It strictly converts kinetic energy into thermal energy.
Right. Heat.
If you slather a highly dynamic system in thick viscoelastic rubber and subject it to continuous vibration, the internal molecular friction will generate massive amounts of localized heat.
And rubber isn't great at shedding heat.
Because rubber is a terrible thermal conductor, the heat cannot escape. The core temperature of the rubber will spike, it will melt, its molecular bonds will degrade, and the isolator will physically disintegrate.
So you basically trade a vibration problem for a thermal failure problem.
Exactly. And the second issue is about high-frequency transmissibility.
Oh, right. Damping actually hurts you at higher frequencies.
Precisely. In the context of a vibration isolation mount, adding damping lowers the peak response exactly at the resonant frequency. That is exactly what you want.
Okay, but
But at frequencies well above resonance, in the isolation region of the spectrum, a highly damped mount will actually transmit more vibration force to the foundation than a lightly damped mount.
That's totally counterintuitive.
It is. The heavy damping stiffens the dynamic response at high speeds, acting like a rigid bridge that passes the high-frequency chatter directly into your delicate equipment.
Wow.
You are intentionally trading low-frequency safety at resonance for high-frequency punishment across the rest of the spectrum. It is an incredibly delicate optimization problem that requires knowing exactly what frequencies you're trying to defeat.
Which means we are flying blind until we know the frequencies. Before we can even begin to apply the right physical fixes like viscous dampers, tuned mass isolators, or stiffness modifiers, we have to actually measure the physical problem. We need hard data from the real world.
Data is everything.
But the data acquisition phase is where the most insidious, totally invisible traps are hidden. Let's look at how we measure this stuff, because if you mess up the measurement, you are doomed.
Data acquisition is the critical translation bridge between the messy physical world of moving metal and the pristine mathematical world of digital computers.
And if that bridge is flawed,
if that bridge is structurally compromised during the measurement phase, every single simulation, calculation, and optimization you do afterward is completely worthless. You are optimizing a fantasy.
So there are 4 major horsemen of bad data that engineers constantly run into when trying to record vibration. Let's ride through them and unpack the physics of why they ruin data. Number 1, clipping.
Clipping happens when the electrical gain on your instrumentation, specifically your signal amplifier or your analog to digital converter, is set too high for the physical environment.
Okay, set too high.
Right. A physical vibration sensor, like an accelerometer, produces a tiny electrical voltage signal proportional to the acceleration. If the physical shock is incredibly violent, it produces a massive voltage spike.
And if that spike is too big?
If that voltage spike exceeds the maximum electrical limit of your recording device, say your system can only handle 5 volts and the sensor sends 8 volts, the system literally cannot record it.
So it just chops it off.
The top and bottom peaks of the analog waveform get violently chopped off flat at the 5-volt line.
I picture it like trying to forcefully walk a 6-foot-tall man into a room with a 5-foot ceiling. His head and his feet are just violently sheared off.
Yeah.
The room cannot contain the reality of his height.
That is exactly what happens electrically, and the mathematical consequences for your analysis are dire. First, by chopping off the extreme physical peaks of the vibration, you are artificially lowering the overall root mean square, or RMS, value of your recorded data.
So your software will tell you the vibration environment is significantly less severe than it actually is in reality.
Exactly. But the second consequence is even worse. Those flat, chopped-off peaks look like perfect, sharp, square waves to your digital analyzer.
And why is that bad?
If you understand Fourier theory, you know that a perfectly sharp square wave can only be created mathematically by summing an infinite series of extremely high-frequency sine waves.
Oh, no.
So the act of coding the data instantly injects a massive amount of fake, artificial high-frequency noise into your data spectrum.
You will spend weeks trying to design a damper to fix a high-frequency vibration that does not exist anywhere in the physical world.
Right. It only exists as an electrical scar created by your bad gain setting.
All right, so if turning the gain too high chops the head off our data and injects fake frequencies, the obvious play-it-safe engineer's fix is just to turn the electrical gain way down, right? Make the voltage tiny so it never clips. But I'm guessing that introduces the second horseman.
It introduces a totally different nightmare, instrumentation noise. This is when your gain is set far too low.
Wow.
Every electronic system in the world, the copper cables, the amplifiers, the silicon sensors, has an inherent electrical noise floor. This is caused by the random thermal movement of electrons inside the circuitry.
And if your gain is too low?
If you turn your gain down too low, the tiny voltage signal generated by the actual physical vibration of your machine becomes smaller than the random thermal noise of your cables.
The real signal is completely buried in a sea of electrical fuzz.
Yep. If you base your structural design on this deeply buried data, you might end up designing a heavy steel stiffener to survive the random thermal static of your amplifier, rather than the actual mechanical vibration of your engine.
Okay, we avoid clipping and we avoid the noise floor. But the third horseman is the big one. It is the ghost maker, aliasing.
Aliasing is a fundamental mathematical failure of the digital sampling theorem, and it is responsible for massive engineering failures.
Let's break this one down slowly.
The physical world is continuous analog data. but computers can only understand discrete digital numbers. When we convert the continuous analog voltage from our sensor into a digital signal, we take discrete point-in-time snapshots or samples at specific time intervals, which we call delta t.
Okay, point-in-time snapshots.
The Nyquist-Shannon sampling theorem dictates a hard mathematical law for this process. To accurately capture a frequency, you must sample at a rate that is at least twice as fast as the highest frequency present in your analog signal.
And for our listeners visualizing the math, the Nyquist frequency limit, FA, equals 1 over 2 times delta t.
Exactly. FA equals 1 over 2 times delta t.
What physically happens in the data if an engineer fails to respect that mathematical speed limit?
If a violent, high-frequency vibration exists in the physical world, say at 10,000 hertz, but your computer is only taking samples at 8,000 times a second, the digital sampling process cannot capture the wave fast enough to define its true shape.
So what does the computer do?
Instead, the mathematics of the digital conversion fold that high-frequency energy backward into the lower-frequency part of your data spectrum. The 10,000 hertz physical vibration masquerades as a low-frequency digital vibration.
I always explain aliasing to people by having them imagine watching an old Western movie where a stagecoach is driving away. The movie camera is essentially taking discrete samples 24 frames per second.
The wagon wheel effect.
Right. If the wooden spokes on the stagecoach wheel are spinning so fast that the rate they pass the camera lens exceeds the camera's frame rate, a terrifying optical illusion happens. The wheel suddenly looks like it has stopped, and then it looks like it is spinning slowly backward even though the stagecoach is moving forward.
It's the perfect visual analogy.
The high-speed physical rotation is aliased into a low-speed visual representation because the camera couldn't sample the light fast enough.
Now, map that exact illusion onto a high-stakes engineering pain point. You are a structural engineer looking at your newly acquired digital data from a prototype test, and you see a massive, terrifying energy spike at exactly 50 hertz.
Okay.
You spend the next 6 weeks and perhaps hundreds of thousands of dollars in fabrication costs designing heavy steel stiffeners and tuned mass dampers to kill a 50 hertz rumble. You install the fix, you run the machine, and the machine immediately tears itself apart.
Because the 50 hertz rumble never existed physically.
Right. The real physical vibration was actually screaming at 10,050 hertz, but because you sampled the data too slowly, the high-frequency energy aliased down and appeared as a digital ghost on your screen at 50 hertz.
You just optimized a multi-million-dollar physical structure to fight a phantom electrical illusion.
Which is horrifying.
A phantom problem that costs millions. But wait, I have to challenge the premise of this entire problem. We are living in an era where data storage is incredibly cheap. Terabytes of solid-state storage are practically free. Processing power is astronomical.
I see where this is going.
Why don't we just mandate that every single sensor samples at 1 billion times a second? Wouldn't oversampling to infinity completely outrun the Nyquist limit and eliminate aliasing while also fixing our fourth horseman quantization error?
In a purely theoretical, frictionless universe, infinitely faster sampling is better. But practically, trying to sample structural data at 1 billion times a second creates immediate, insurmountable physical bottlenecks.
Really? Like what?
First, analog to digital converters that can run at gigahertz speeds while maintaining high bit resolution are incredibly expensive. They draw massive amounts of power and they generate immense heat. You cannot stick a liquid-cooled supercomputer on the wing of a fighter jet.
Okay, that's fair.
Second, while the hard drives might be cheap, the transmission bandwidth is not. If you are trying to push billions of data points per second through a telemetry antenna from a rocket tearing through the ionosphere, or through a sonar cable from a moving submarine, you will instantly saturate your transmission lines and lose the data stream entirely.
So you literally can't get the data out.
No, you can't. And third, as you mentioned, there is the quantization error.
Right, let's unpack the fourth horseman, quantization error.
Quantization error is the digital round-off noise inherently caused by the analog to digital converter's bit resolution. It is the staircase effect.
The staircase effect.
Yeah. An analog voltage is a perfectly smooth, continuous curve. But a 16-bit digital converter only has exactly 65,536 discrete microscopic voltage steps it can use to represent that curve.
It is like trying to trace a smooth ramp using Lego bricks.
That's exactly it. The true analog voltage flowing from the sensor almost never lands perfectly flat on one of those discrete Lego steps, so the computer is forced to round the value up or round it down to the nearest available step.
Which means it's constantly slightly wrong.
Right. This tiny continuous rounding error introduces a permanent underlying floor of white noise into your data. If you try to sample at 1 billion times a second, you are forcing the computer to generate billions of microscopic round-off errors every second, drastically raising the noise floor.
So the standard practice isn't infinite sampling.
The standard professional engineering practice is not to rely on infinite digital sampling. It is to use a physical, analog, low-pass anti-aliasing filter placed directly in the circuit board right before the digital converter.
So you use an analog circuit as a bouncer at the club. It physically scrubs away and blocks any high frequencies above the Nyquist limit from entering the room before they can even reach the digital converter and cause ghosting.
Brilliant. It's the only reliable way.
Okay, so let's assume we survived the gauntlet of the Four Horsemen. We set our gains perfectly to avoid chopping heads off with clipping. We stayed well above the thermal noise floor. We used our analog anti-aliasing filters to kill the ghosts. And we have enough bit depth to minimize the staircase effect.
We have clean data.
We have successfully captured clean, uncorrupted, pristine digital data. We are still just staring at a massive, unintelligible, jagged, squiggly line of voltage over time on a computer screen.
Time history data.
Staring at that chaotic time history data doesn't actually tell me how to physically fix the brackets on my engine. How do we decode that squiggly line?
You have hit the exact transition point between data acquisition and data analysis. Staring at a complex time history trace is like looking at a bowl of mixed paint and trying to figure out exactly what colors went into it.
It's impossible to tell by just looking at it.
It rarely tells an engineer the specific physical frequencies that are causing the damage. To extract actionable information, we have to fundamentally shift our perspective. We have to move out of the time domain and translate the data into the frequency domain.
And we do this using a mathematical algorithm called the fast Fourier transform, or FFT.
Exactly.
I love the concept of the Fourier transform. It feels like real-world magic. I think of it like unbaking a cake.
Unbaking a cake.
Yeah, you have this incredibly complex baked time history cake that represents the total vibration. The FFT algorithm takes that cake, unbakes it, and prints out a receipt telling you exactly how much flour, sugar, and eggs went into it.
I like that.
Or, in our engineering case, it tells you exactly how much 10 hertz energy, 50 hertz energy, and 1000 hertz energy combine to create that complex, chaotic rattle.
Unbaking the cake is an excellent way to visualize the theorem that Fourier developed over 200 years ago. The FFT algorithm mathematically decomposes the complex, jagged waveform into a vast spectrum of individual, perfect sine waves, each with its own specific frequency and its own specific amplitude.
But this is where engineers must be incredibly careful, right?
Absolutely, because you have to choose the right mathematical translation tool based on the specific type of vibration environment you identified back in step 1.
Okay, let's revisit that. What if the data is deterministic?
If your data is deterministic, like the steady, predictable hum of a diesel generator, you use a simple line spectrum. When you run the FFT on deterministic data, the output will show distinct, sharp, vertical spikes at specific, discrete frequencies.
It tells you exactly how fast the generator is spinning and exactly what harmonics it is generating.
Right. But if the environment isn't a steady hum, what if the data is random vibration? The wobbly shopping cart full of bowling balls rolling over cobblestones.
Yeah, what then?
If you try to use a simple line spectrum to analyze random vibration, the output is entirely useless. Because random vibration is chaotic, the amplitudes are constantly shifting millisecond by millisecond, and the energy is smeared continuously across a massive broad band of frequencies.
There are no clean spikes.
There are no clean, distinct spikes to look at. For random data, you must abandon the line spectrum and translate the data using power spectral density, or PSD.
Let's really break down the mechanics of PSD, because the acronym alone sounds deeply intimidating to a lot of junior engineers. What is it actually calculating?
Power spectral density is a statistical tool. Mathematically, it calculates the limiting mean square value of the vibration, which relates directly to the physical energy or power contained in the signal, and divides that energy by the frequency resolution bandwidth.
So you're looking at energy distribution.
You are essentially looking at how the total destructive energy of the vibration is distributed across the entire frequency spectrum as the measurement time approaches infinity. You have to stop thinking about exact amplitudes.
Right, because it's chaotic.
Instead of a line spectrum saying there is exactly 2 Gs of peak acceleration precisely at 50 hertz, a PSD plot tells you There is a specific density of continuous acceleration energy concentrated in the frequency band around 50 Hz.
Yeah, the total energy is.
The area under the curve of a PSD plot gives you the overall root mean square energy of the entire chaotic environment.
But just like measuring the data had traps, the mathematical translation process itself has traps, right? What are the processing errors engineers make when they run these FFTs and PSDs?
The most common and deceptive processing error is leakage error.
Leakage error, what's that?
When you command a computer to perform an FFT, the underlying mathematics inherently assume that the finite 10-second sample of data you gave it repeats itself infinitely forever in both directions.
It pretends your small clip is the whole universe.
Exactly. But if the jagged voltage at the exact end of your 10-second data sample does not perfectly line up with the voltage at the exact beginning of the next hypothetical repeated sample, it creates an artificial jagged discontinuity.
And the math hates a sudden jump.
The math algorithm panics at this sudden discontinuity, and it tries to fix it by leaking the true energy from the actual frequency into all the neighboring frequencies. A sharp, distinct peak of energy gets smeared out into a wide, shallow mound.
So you lose your resolution. How do you fix that?
Engineers have to actively counter this mathematical artifact by applying a digital window to the data before running the FFT. A window, like a Hanning or flat-top window, is a mathematical curve that forces the very ends of the data sample to taper smoothly down to zero, eliminating the discontinuity and stopping the energy from leaking.
Okay, so that fixes leakage. And beyond leakage, there's the fundamental, almost philosophical balancing act between random errors and bias errors when you are setting up your PSD parameters.
Yes, this is the ultimate compromise in digital signal processing. It is almost like the Heisenberg uncertainty principle for vibration analysis.
How so?
When you process a PSD, you want the plot to be smooth and accurate. To reduce random error, which is the statistical variance that makes your PSD plot look like a jagged, noisy, unreadable mountain range, you need to average a massive number of data samples together over a very long period of time.
So longer averaging means smoother data.
Right. But to reduce bias error, which is a lack of resolution that causes the algorithm to artificially blunt and underestimate the true destructive height of sharp resonance peaks, you need to set a very narrow frequency resolution bandwidth. The mathematical reality is that you cannot have both infinite averaging time and an infinitely narrow resolution bandwidth. You have a finite amount of recorded data. You are forced to balance the two errors based on the physical realities of what you are trying to find.
So if you need a long averaging time to smooth out the random error, I have to ask the difficult, messy reality question.
Hit me.
What does this all mean for non-stationary data? If the physical environment is constantly changing, like our rocket accelerating through the atmosphere and experiencing maximum dynamic pressure, how can you possibly take an average over a long time period without completely blurring out and hiding the exact momentary extreme events we are trying to study?
That is the ultimate paradox of non-stationary data analysis, and it is incredibly difficult to solve.
Because if you average the whole launch...
If you average the rocket's vibration over a full 60-second time period to get a smooth curve, you completely smooth out and erase the violent 3-second transient peak of maximum aerodynamic pressure that might actually tear the payload apart. The math hides the danger.
And if you average too short?
If you average over too short of a time period, say just half a second, your statistical confidence drops to near zero, the random error skyrockets, and your spectrum just looks like meaningless static.
So how do you win?
The modern computational solution is to use a running average, creating what is called a waterfall plot, or a spectrogram.
Ah, waterfall plot.
You slice the non-stationary time history data into very short, overlapping, pseudo-stationary segments. You compute an instantaneous frequency spectrum for each tiny slice, and you stack them sequentially in a 3D plot with time on the z-axis.
That sounds computationally heavy.
It requires immense computational power, but it allows an engineer to visually see how the frequency content physically shifts dynamically through time as the rocket accelerates without blurring the critical extreme peaks into statistical oblivion. That is how we decode a constantly changing environment.
Okay, so we've translated the continuous hums, the random rattles, and the shifting environments. We know how to unbake the cake using FFTs and PFTs. But what happens when the event isn't continuous?
You mean shock?
Right. While vibration analysis looks at ongoing continuous environments where energy builds up over time, shock analysis requires an entirely different engineering mindset. The event is over, the explosion has happened, the package has hit the concrete before the internal structure even realizes what hit it. How do we model the sudden violence?
Mechanical shock is defined purely by its suddenness and its severity. It is a transient excitation.
Transient.
Right. When we analyze continuous vibration, we care deeply about the steady state response, how the structure behaves after the forces have settled into a rhythm. In shock analysis, there is no rhythm.
So what do we care about?
We care about the primary response, which is the massive deflection that occurs precisely while the shock pulse is actively happening, and we care about the residual response, which is the free, unforced vibration of the structure ringing out like a bell after the external shock force has completely passed.
And to standardize how we test for these complex, chaotic real-world impacts, we model these shocks using idealized classical physics shapes, right?
Yes. To make laboratory testing repeatable and mathematical analysis possible, we distill complex, real-world impacts into classical shock forms.
Like what?
The most extreme theoretical form is the acceleration impulse. We model this mathematically using the Dirac delta function,
The delta function.
which describes an infinitely high acceleration occurring in an infinitesimally small fraction of time, delivering a massive specific velocity change instantly. In reality, nothing is truly instantaneous, but a hard hammer strike on an anvil gets very close.
Okay, and another form.
Then there is the step velocity, where the foundation of a structure instantly changes speed, like a car crashing into a concrete wall.
Makes sense.
And in the massive realm of industrial drop testing, making sure your laptop survives falling off a desk, we frequently use the half-sine pulse. This is a smooth, rounded impact profile that mathematically looks exactly like the top half of a sine wave. It models an object hitting a slightly compliant surface, like a cushioned floor.
But just looking at a time history plot of a half-sine drop pulse, just seeing that it was a 50G impact that lasted for 11 milliseconds, doesn't actually tell an engineer if the delicate silicon microchips on the internal circuit board will fracture.
No, it doesn't.
To understand the actual physical damage potential, we have to translate that pulse using the SRS, the shock response spectrum. This is another area where I see massive confusion in the industry.
It is arguably the most profoundly misunderstood tool in all of dynamic structural analysis. I see engineers misuse it constantly.
Let's clear it up then.
Let's establish a foundational rule right now. The shock response spectrum does not show the shock itself. It does not show the frequency content of the input pulse. It is not an FFT of the impact.
So what does the SRS actually show?
The SRS calculates the absolute maximum physical response of a theoretical series of single degree of freedom structures to that specific shock.
Wait, a theoretical series?
Yeah, imagine you have a rigid steel baseplate. On that baseplate, you mount a row of 100 tiny, independent, theoretical mass spring systems. Each one is tuned to have a completely different natural frequency. The first one is 10 hertz, the next is 20 hertz, all the way up to 10,000 hertz.
Okay, I'm picturing this row of springs.
Now, you subject that entire baseplate to a violent physical shock, like an 11 millisecond half-sine drop. As the shock hits, all those tiny springs compress and expand wildly.
Right.
The SRS algorithm calculates and records the absolute maximum peak response, the maximum displacement velocity or equivalent static acceleration that each individual spring mass system experienced, either during the primary shock or during the residual ringing afterward.
Just the maximum P.
It's just the peak. You then plot those maximum peak responses on the y-axis against the natural frequencies of the systems on the x-axis. That resulting curve is the shock response spectrum. The underlying mathematics for calculating this involves solving a complex convolution integral called the Duhamel integral for every single one of those theoretical mass spring systems.
This brings us directly to the massive misconception that ruins shock testing and destroys millions of dollars of hardware. It is the error of confusing the Fourier spectrum with the shock response spectrum.
Yes.
I look at it this way. The Fourier spectrum is studying the punch. It tells you the mass, the velocity, and the exact frequency content of the steel wrecking ball swinging at a building. It analyzes the weapon.
Excellent analogy.
But the SRS is studying the bruise left behind. It tells you exactly how far the building's internal support beams physically bent and yielded when they got hit by that weapon. They are two completely different perspectives.
That is an outstanding, highly accurate analogy. The Fourier spectrum breaks down the composition of the input energy. The SRS measures the resulting damage potential to the structure. Engineers constantly mix these two up because both plots have frequency on the x-axis.
You just grab the wrong tool.
An engineer will take a shock pulse from a test, run a standard FFT on it, look at the frequency content of the pulse itself, and then try to design their circuit board to avoid the frequencies present in the pulse.
But the board doesn't care about the input frequencies.
Exactly. The internal structure doesn't care about the mathematical Fourier spectrum of the input. It strictly cares about how far its own springs are physically forced to deflect. The SRS curve tells you exactly what the maximum equivalent static acceleration will be for a structure of any given natural frequency.
If you design your hardware based on the Fourier spectrum of the shock instead of the SRS of the shock,
You are optimizing the mass and stiffness for the wrong parameters entirely, and your board will snap in half upon impact.
but let me challenge the entire foundational concept of the SRS. If the entire shock response spectrum relies on mathematically simulating a bunch of incredibly simplified, independent, single degree of freedom mass spring systems sitting on a theoretical base plate,
Right.
how can that simplistic model possibly give us accurate, actionable design parameters for something as incredibly complex as a spacecraft satellite or a naval submarine? A submarine pressure hull isn't a simple coil spring.
It seems wildly counterintuitive that such a simple model works for such complex structures, but it works flawlessly because of the theory of modal superposition that we discussed earlier.
Back in section 2.
Yes, a naval submarine is vastly complex, but mathematically, its entire dynamic response to a shock wave can be broken down into a linear combination of its independent normal modes. Each one of those complex bending and twisting modes behaves mathematically exactly like one of those simplistic, theoretical, single degree of freedom mass spring systems.
That's incredible.
If you run a modal analysis and determine the natural frequencies of the submarine's critical internal decks and bulkheads, you can then look at the SRS plot generated by the underwater explosive shock wave.
And then what?
You simply find the frequencies of your bulkheads on the x-axis of the SRS plot, and you can immediately read the exact maximum peak acceleration each bulkhead will experience on the y-axis.
Just reading it right off the chart.
It gives you the absolute worst-case boundary conditions for your structural design without having to run an incredibly computationally expensive full-scale transient finite element analysis of the entire submarine for every possible explosion scenario.
That is the immense power of translating the data properly. It simplifies the chaos. Okay, we have thoroughly mapped the theory. We've navigated the invisible data measurement traps of aliasing and clipping. We've translated the time history data using PSDs for random vibration and the SRS for sudden shocks.
We've covered a lot of ground.
Now, we can finally walk through the ultimate step-by-step approach to taking all this math and fixing the physical design in the real world. Let's talk about step-by-step optimization.
This is where the mathematical rubber meets the physical road. All the theory we just discussed feeds directly into a rigid four-step methodology for controlling shock and vibration in practice. If you skip a step, you fail.
Okay, step 1, identify.
You must correctly categorize the excitation. Is your input a deterministic hum from a motor, a random broadband rumble from turbulence, or a transient shock from a drop? You cannot mathematically apply a PSD analysis to a predictable engine vibration, and you cannot use a line spectrum FFT to understand a half-sign drop. If you misidentify the enemy, you will use the wrong weapon.
Step 2, measure.
Step 2 is capturing clean, uncorrupted data from the physical environment. You must meticulously set your electrical gains properly to avoid clipping the high peaks or drowning the signal in the thermal instrumentation noise floor.
And handle the aliasing.
And you absolutely must ensure your hardware is using analog low-pass filters to enforce the Nyquist limit and prevent high-frequency aliasing from creating digital ghosts in your spectrum.
Step 3, analyze.
Use the correct domain translation tool. If you are dealing with a steady-state continuous vibration, move from the time domain to the frequency domain using the fast Fourier transform. Use line spectra to analyze deterministic rotating equipment, and use power spectral density to analyze random aerodynamic turbulence.
And watch out for errors.
And when using PSD, carefully balance your bias and random errors using the appropriate mathematical windowing and averaging times. If the event is a sudden transient shock, completely ignore the FFT and use the shock response spectrum to understand the maximum damage potential to your specific modes.
And finally, step 4, control. This is implementing the physical fix on the hardware. From all the engineering sources and case studies we review, we can group these physical fixes into 3 distinct buckets of action.
Bucket 1 is reduction at the source. This is always the best, most direct, and most efficient method.
Fix the problem where it starts.
Exactly. If a massive rotating cooling fan is vibrating and shaking your chassis, you don't add heavy structural supports. You balance the moving mass of the fan. You add or subtract tiny weights to the rotor blades until the centrifugal forces completely cancel each other out.
Like balancing a tire on a car.
Right. If a gear bearing is rattling violently, you tighten the tolerances and fix the clearances. You alter the operational parameters to stop the destructive vibration energy from ever being generated in the first place.
But sometimes you simply cannot touch the source. You cannot ask a turbulent ocean to calm down, and you cannot ask the aerodynamic pressure on a rocket to stop. That leads us to bucket 2.
Bucket 2 is isolation. You place a highly engineered dynamic barrier between the violent source and the delicate receiver.
Like mounting a hammer.
Yeah, if a massive, heavy forging hammer is shaking the concrete floor of a manufacturing plant and destroying nearby precision milling machines, you mount the heavy hammer on massive pneumatic shock isolators to protect the building.
And the reverse.
Conversely, if you have highly delicate servo electronics inside a naval ship that is experiencing massive hull shock from crashing through waves, you mount the delicate electronics on specialized wire rope shock isolators to protect them from the ship. You physically break the transmission path of the energy.
And if you can't balance the source and you don't have the space to isolate it, you are left with bucket 3, reduction of the response.
This is where you are forced to physically alter the structure of the receiver itself. You can change its internal natural frequency to avoid the resonance wrecking ball by welding on stiffeners to increase the K value or bolting on mass to increase the mem value.
Or adding damping.
You can add energy dissipation by applying thick layers of viscoelastic damping materials to the housing to turn the kinetic energy into heat. Or you can attach an auxiliary dynamic vibration absorber or a tuned mass damper.
That one is a brilliant engineering trick.
It really is. You attach a secondary small mass spring system to your main structure, mathematically tuned to vibrate completely out of phase with your main structure's movement.
So they fight each other.
As the main structure moves up, the tuned mass damper slams down, applying a counteracting inertial force that completely cancels out the motion of the primary structure.
These practical control steps always lead to some common questions we get from the field regarding standardization and testing. Engineers want to know how to validate that these physical fixes actually work before they ship the product.
Oh, the standards question.
Yeah. What about relying on military standards like ISO TC 108 and MIL STD 810? People constantly ask, should we just use the generic vibration test specifications published in these manuals for our components to save testing time and money?
The definitive, industry-wide answer in modern structural engineering is absolutely not.
Not at all.
No. While documents like MIL STD 810 and the ISO standards provide excellent, rigorously proven guidelines and procedures for exactly how to operate a shaker table or how to mount a sensor, the modern standard practice is to completely avoid using their generic baseline test levels.
But people used to do that.
In the past, engineers would just pull a generic highway transport vibration curve from a dusty manual and test to that. But the modern mandate is tailoring. You must tailor your tests to your specific, measured physical environment.
So you have to go out and get the data.
You must physically acquire raw data from the actual operating environment of your specific hardware-put sensors on the actual Humvee, driving through the actual mud, analyze it using the exact steps we just outlined, and derive a custom PSD test specification that mathematically replicates your true localized field conditions.
Because generic tests are risky.
Using generic pre-published tests is a massive risk. They will either severely undertest your part, leading to catastrophic field failures because your specific environment was harsher, or they will severely overtest your part, forcing you to overdesign, overstiffen, and add massive amounts of unnecessary weight and cost to survive a vibration that the part will never actually see in reality.
Let me bring up a messy reality question about that third control bucket. Tuned mass dampers. We talk about how you can theoretically tune a secondary auxiliary mass to perfectly counteract your primary vibration. But paper is patient, and steel isn't.
That's the truth.
How do we actually dial in a tuned damper in practice, out in a freezing oil field or inside a hot engine compartment, when variables like ambient temperature completely change the molecular stiffness of our rubber isolators? We already established an hour ago that dynamic stiffness is a massive trap. If the temperature drops, the rubber gets harder, the K value changes, and the math falls apart.
That is the ultimate crucible of mechanical engineering. Reality ruining your math. You calculate the perfect tuned mass damper on your pristine whiteboard. You install it in the field, it works perfectly at room temperature, and then a cold front rolls in.
And then,
Suddenly, it is 20 degrees colder. The polymer chains in the rubber spring of your damper stiffen up. The dynamic K value skyrockets. The natural frequency of the damper shifts away from the frequency you were trying to cancel, and your damper is now completely out of tune and entirely useless.
or worse.
Or worse, it starts amplifying the main structure's vibration. In practice, seasoned engineers handle this brutal reality by designing broadband dampers.
Broadband dampers.
Instead of tuning the absorber to an impossibly narrow, sharp frequency peak, they intentionally inject a specific amount of viscous or structural damping directly into the absorber itself. This added damping flattens out the mathematical response curve.
Okay, so it covers more ground.
The damper becomes slightly less effective at the absolute perfect peak frequency, but its cancellation effect is smeared out over a much wider frequency band. So even if environmental temperature shifts the rubber stiffness and moves the natural frequency left or right, the damper stays within its broad, effective operating window.
That's so smart.
It is the classic engineering compromise, trading peak theoretical performance for robust, fail-safe, real-world reliability.
Trading whiteboard perfection for real-world reliability. That is exactly what mechanical engineering made simple is all about. So what does this deep dive mean for you, the listener, the one actually designing these parts?
It means that the chaotic, destructive mechanics of shock and vibration are not black magic. They are not random acts of destruction. They are governed by rigid physical laws that can be understood, measured, and completely controlled as long as you respect the mathematics and avoid the invisible traps.
Exactly. The physics are impartial. Whether you are identifying the difference between deterministic inputs and random chaos, making sure your dynamic stiffness calculations account for polymer locking, actively respecting the Nyquist limit with analog filters during your digital data acquisition to prevent aliasing, or ensuring you use the shock response spectrum instead of a Fourier transform to measure the actual structural bruising of a transient impact, the core principles hold true.
By systematically, rigorously moving through the 4 steps of identification, measurement, analysis, and control, you can mathematically tame any dynamic environment.
I want to leave you with a final provocative thought to mull over as you head back to your CAD models and finite element simulations. Throughout this entire deep dive, we have been talking about passive structural systems. Passive masses, passive springs, fluid dashpots, pieces of hysteretic rubber.
Things that just sit there and react to the physics imposed upon them.
Exactly. But the industry is moving rapidly toward the era of active vibration control. We are talking about integrating smart materials, piezoelectric sensors, and high-speed electromagnetic actuators directly into the load path that can mathematically adapt their damping properties and stiffness in real time based on live data.
Active control is the future.
Will the static passive masses and springs we painstakingly design today become entirely obsolete in a decade? Imagine a near future where a multi-million-dollar turbine can actively listen to its own internal frequencies, anticipate a chaotic random excitation from the environment, calculate the exact Fourier transform of a threat in microseconds, and physically fire opposing electromagnetic actuators to completely cancel out the motion before the wrecking ball of resonance even has a chance to form.
It's an incredible thought.
The predictable metronome and the wobbly shopping cart on the cobblestone street might both be entirely defeated by mechanical structures that can mathematically think, anticipate, and violently push back. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.